So this is the Laplace transformation that we're doing. We got an example in class the other day, and this was exactly where the resistance was 2 ohms, the inductance was 5 Henry, because inductance is measured in Henry, and the capacitance was 0.2 farads. Now we know that these are all in parallel. That means that we need to add the total current, because the currents will be different in them. For the resistance, here's the total current. So you have IT being equal to IRT plus ILT plus ICT, all of them with respect to time. Now we know that IRT, the VR, is in the opposite direction than what it should be for it to be positive. So therefore we have 0 minus VRT over 2, because the voltage drop across here is 0 minus here, which is negative VR due to the direction of the voltage, over 2, which is also equal to VRT over 2, and that is the current for the resistor. Now for the inductor, we already got those equations in class. Those are quite simple right here. This is the equation for the inductor. These are charging equations where ILT is equal to 1 over L T0 V T dt, and that is the charging equation for an inductor. Now what we're going to do is write down the total charge, the total inductance right here, ILT, which would have been equal to 1 over L T0 VT dt. And we also had an inductance, an initial inductance, which was equal to -1 amps. So we're going to put plus IL0. This was before the system was had been turned on to be charged. And then, so this is the equation for the inductor in this particular diagram. Now we're gonna find the equation for the capacitor. ICT is equal to, and we had the charging equations from before. ICT is equal to C dV dt with respect to time, which simply means we just write that down. It's equal to C dV dt t plus we have a voltage. It had an initial voltage, because we all know that the voltage in a capacitor, before it has been charged, it can have an initial voltage, and it can have a volt of 0 if it has never been charged before. But obviously this capacitor was already charged, so it was discharging a 4 volt, a value of 4 volts. So we're going to add that to VC0 right here, and then this now is the capacitance. So this is the value for the capacitor, or the equation for the capacitor. What we need to do is substitute the resistor equation, the inductor equation, and the capacitor equation into IT. And when we substitute that into IT, we're gonna try to find VRS. So then IT is equal to VRT over 2 plus 1 over L T0 VT dt plus IL0 plus C dV dt t plus VC0. What's gonna happen now is that we're gonna plug in the Laplace transformation for this, and we know that the Laplace transformation is different for each component that we have. For a constant is different, for the integral is different. But those we get on a table, so we won't have to worry about remembering the value for those or anything of the sort. We're just going to substitute them from a simple table that we got in class. Now this is the table. Constant, this is a constant. The IL0 equal to IL0 over S. The integral equal to VRS over S. As you can see here, we have an integral right there. So we'll just substitute that for S and take out the integral. And we have the dr over dt right here. So then we just substitute all of these into the equation, which would have given us that IT is equal to VRS over 2 plus 1 over L VRS over S plus I0, which was the initial inductance, which is IL0 over S, plus the capacitance, which is S VRS minus VR0, which is initial charge or voltage discharge of the capacitor. All of this is equal to 0 by Kirchhoff's current law. Now what we need to do is to multiply this equation through by 10s, because this is 5 and the inductance that we're going to get, we're going to substitute into this equation, will also be 5 from the diagram that was drawn. The diagram that was given, the inductance was 5 henries. And also this equation right here can be misinterpreted because the capacitance was supposed to be times by all of this, which was not done. So we need to have a bracket here and have times the capacitance. Correct? Just as here in the capacitor equation, it should have been a bracket around this. That's the bracket what's around, because the Laplace transformation takes this into consideration. So when you substitute this into the Laplace into this, then what happens is that the VC0 goes into here, so it's C times all of that in there. Then from there we know that the new equation is VRS over 2 plus 1 over 5 VRS over S plus negative 1 over S plus 1 over 5 SVRS minus VR minus, not VR0, because we had the value for that, which was 4 volts, equal to 0. Now we want the equation to be in terms of VRS. So how can we get this equation to be in terms of VRS? First we have to group like terms, and in order to group like terms, we'd like to make this equation much simpler by multiplying through by 10s, since we have 5 and 5 right there and s is under the bottom, so we want to make all the denominators 1. So then, and this is 2, so we can't multiply 2 by 5s because we'd still have that 2 down there, so we'd have to multiply through by 10s, which would give us a result of this. When we multiply through, right here, multiply through by 10s, I'll highlight it that you can see it, multiply through by 10s, then what we'll get is this equation right here. But that equation is not necessary. What we need to do is factor out to VRS. When we factor out VRS, this is what we get. So it's just a matter of dividing through by this highlighted piece to get the VRS. Now the value of VRS is what we're going to be using to do a partial fraction in order to get the Laplace form that we're looking for. And this is it right here. VRS is now equal to 10 plus 8s over 5s plus 2 plus 2s squared. And when we factorize this quadratic, we'll get this right here. Now we know for the Laplace form, this is f of t. This form is f of t, and this is f of s, which we're going to get it into. When we do partial fractions, what we have is this, which we arrived at being equivalent to a over the both denominators separately. And then find the LCM, equate them as we did before, and let s equal to minus 2, therefore a equal to 0 and b found to be 2. And then s equal to minus a half, therefore b found to be 0 and a is equal to 4. Now what we're going to do after that is to find the exact, we're just going to put it into the form that it needs to be in, so in order to find the equation. So it's going to be 4 over 2s plus 1, the equivalent, plus 2 over s plus 2. But as we said before, we want it into this form. We want to get it back to this form right here, to the f of t form. But you have to have the denominator being s plus a. As we can see here, the denominator for right here is not in s plus a. So all we have to do for this is really simple. Don't worry, it may look hard, but it's really simple. We just factor out the 2 from there. What's gonna happen then? We're gonna have 4 over 2 s plus a half plus 2 over s plus 2. What do you know? 2 into 2, 1 time, 2 into 4, 2 times. Now, since we know that we need to get it to this form, let's try to get it to this form. This is now in f of s form, which is the Laplace form, and we need to get it to f of t. Therefore, we're going to use the z. But as you can see, we're going to use this for the first part, which is equal to 2 e to the minus half t plus this one now, a is equal to 2, so the a from here is equal to 2, and the z is equal to 2, so 2 e to the minus 2t, and this is the answer in f of t, and that's the Laplace transformation that we're going to use today. Hope you understand and see that this is f of t now and not f of s as this was before. The top equation was in f of s.
Don't know.